Hello, and welcome to Differential Equations. This is Lecture 12, Differential Operator Notation. Last time, we saw the following theorem. If the nth order linear ODE, right, given by dy to the n, dt to the n, plus pn minus 1, dn minus 1 of y, tn minus 1, so on, e naught y equal to 0, has constant coefficients and its characteristic polynomial as the factorization to the characteristic polynomials r to the n plus pn minus 1, r to the n minus 1, so on. And let's say that it factors as r minus r1 r minus r1 to the k1 times r minus r2 to the k2, and so on until you get to r minus r, say, rl to the kl, right? So here the fundamental theorem of algebra tells us that k1 plus up to kl, these are the multiplicities of different roots that they have to add up to n. Then, okay, so for each of these, if I'm going to get n different differential solutions, then I need to get k1 solutions corresponding to r1, k2 solutions corresponding to r2, and so on. So the k1 solutions corresponding to r1 are e to the r1t, then t e to the r1t, and so on until you get to t to the k1 minus 1 times e to the r1t. Then the ones corresponding to r2 would be e to the r2 times t, and then t e to the r2 times t, until you get to t to the k2 minus 1 e to the r2 times t, and so on until rl, you'd have e to the rl times t, t e to the rl times t, and so on until t to the kl minus 1 e to the rl t. Right? So there we go. I have now written down n different solutions to this differential equation, and these make up a set, a linearly independent set of n solutions to the ordinary differential equation, right? And as soon as you have n linearly independent solutions to your ordinary differential equation, linear ordinary differential equation, then the general solution is just a linear combination of those solutions. Okay, so that's what we saw last time. This time, we're going to do two things. We're going to introduce notation. It's going to be very useful going forward. And we want to study the structure of solutions of non-homogeneous linear equations with constant coefficients. Okay, so let's start with the, I'll leave that. Let's start with the notation. Okay, so when we're considering the differential equation like second derivative of y with respect to t plus 5 times the first derivative with respect to t plus 4y equals 0, it is useful to think of the left-hand side as a differential operator acting on the function y. So here we would define, say, curly L to be second derivative plus 5 times first derivative plus 4. And then we could write the equation in the more compact form as just looking for Ly equal to 0. We're looking for the y's such that Ly is equal to 0. Okay, so a differential operator like this L is a particular type of map that takes functions to functions. We're not going to go into it, but what's special about differential operators is that they don't extend support. So they're linear maps that take, well, the ones we're going to look at are linear maps that take functions to functions. And if a function is 0 on some open set, then you apply the operator. What you get is still 0 in that open set. That's what characterizes differential operators among those maps. Here, so just to keep going with this L, notice that if you were to apply L to e to the t, this would just say apply this to the function e to the t. So you would take two derivatives, nothing happens. Then 5 times when you take one derivative, and then multiply this 4 here at the end. This is multiplication by 4. So L of y ends with 4 times y. So here I would end up 4e to the t. So altogether, this would just be 10e to the t, right? So it's a map that takes a function to a function. We saw last time, one way of getting the characteristic polynomial or of motivating it is to notice that if you plug in e to the RT, then okay, you would just get r squared e to the RT plus 5r e to the RT plus 4 e to the RT. And so you could factor out a polynomial, namely the characteristic polynomial times an exponential e to the RT. You could also plug in a polynomial, say you just plug in t to the n, then you'd get n times n minus 1, t to the n minus 2 from this first term, plus 5 n t to the n minus 1 from the second term, plus 4 t to the n from the third term, and so on. Okay, L is called a linear operator if for any two functions y1 and y2, and any constant a, we have L of a times y1 plus y2 is equal to a times L of y1 plus L of y2. Every linear homogeneous ordinary differential equation can be written as L of y equal to 0 for some linear differential operator. Yeah. And the corresponding non-homogeneous ODE is L of y equals f for some function f, often called the forcing term. The operator notation is especially useful when we want to talk about differential equations abstractly and not discuss a particular equation. Let's do an example. In fact, we'll now do several examples of what we talked about last time using this new notation. So for example, if, let's say, curly S is the operator 2 derivatives plus 5 times 1 derivative plus 6, then the ordinary differential equation S of y equal to 0 has characteristic polynomial r squared plus 5r plus 6, which factors as r plus 2 times r plus 3, right? So we see the roots of this polynomial are minus 2 and minus 3. So e to the minus 2t and e to the minus 3t are solutions of sy equal to 0. And the general solution is a times e to the minus 2t plus b times e to the minus 3t, where a and b are arbitrary constants. Okay, let's do another example. Right, so this was the simplest case where the characteristic polynomial has distinct roots. Let's do an example with repeated roots. So let's say curly t is the differential operator that takes 2 derivatives, subtracts 4 times 1 derivative, and then adds 4. So then the ODE t of y equal to 0 has characteristic polynomial r squared minus 4r plus 4, right, which factors as r minus 2 squared. Okay, so since we have repeated roots, what we'll do is we take e to the 2t as one of our solutions, right? And then to get another linearly independent solution, we multiply it by t times e to the 2t. These are solutions of t of y equal to 0. And because they're linearly independent, and the general solution is a e to the 2t plus b t e to the 2t. Okay. Let's now allow complex roots. So let's say that curly r is a differential operator that takes two derivatives, then subtracts 4 times one derivative, and then instead of adding 4 like we did in the previous example, we'll add 13. And the ODE r of y equal to 0 as characteristic polynomial r squared minus 4r plus 13, which we could write as r minus 2 squared plus 9. And then if we introduce complex numbers, that's the difference of squares. So you'd have r minus 2 minus 3i times r minus 2 plus 3i. Okay, so we have two solutions. So the exponentials will be solutions of the ordinary differential equation. So here we have e to the 2 plus 3i times t and e to the 2 minus 3i times t. These are solutions of r of y equal to 0, and they're linearly independent. So the general solution is a times e to the 2 plus 3i times t plus b times e to the 2 minus 3i times t. Right, using Euler's formula, we know that another way of writing the general solution since e to the 2 plus 3i times t is equal to e to the 2t times cosine 3t plus I times sine of 3t, and e to the 2 minus 3i times t is e to the 2t cosine of 3t minus I sine of 3t. Is as c times e to the 2t cosine 3t plus d times e to the 2t sine of 3t, where c and d are arbitrary constants. Okay, what if you have repeated roots and they're complex? Let's do an example of that. So to guarantee that we have repeated complex roots, let's just stick with this linear operator r. All right, so r is going to be the same operator, but we're going to consider the ordinary differential equation r squared y equal to 0. So here r squared y, I mean r composed with r. So r of y equal to 0. Okay, so that ODE has characteristic polynomial the same one as we had in the previous example, only squared. So it's going to have the same factorization as in the previous example, but with each factor squared. Okay, so because of that, the solutions that we talked about at the top of the class would be e to the 2 plus 3i t, and then t times e to the 2 plus 3i t. Then also 2 to the e to the 2 minus 3i t, and t times e to the 2 minus 3i t. These are solutions of r squared y equal to 0. And the general solution is just an arbitrary linear combination. So a times the first one plus b times the second one plus c times the third one plus d times the last one. But another way of writing the general solution would be as, let's say, e times e to the 2t cosine 3t plus f e to the 2t sine of 3t plus g t times e to the 2t cosine 3t plus h t e to the 2t sine of 3t. Okay, so that's what happens if you have repeated complex roots. Then on the one hand, you can treat them just like you would repeated real roots, right? The general solution is just this. But then if these roots, if you have conjugate complex roots, then you can always switch from using complex exponentials to using sines and cosines. Okay. So next, let's talk about non-homogeneous linear ordinary differential equations. Okay. So here's the structure theorem for solutions. And here you'll see it's really useful to use the operator notation. Suppose L is a linear differential operator. For this theorem, I don't need it to have constant coefficients, just that it's linear. So suppose L is a linear differential operator and y sub part for particular, this is some solution of the non-homogeneous ordinary differential equation L of y equals f. Right? So we call y part the particular solution. Right? It need not involve arbitrary constants. Right? So we're just looking for any solution. If you found a solution that has arbitrary constants, so you really found multiple solutions, go ahead and choose the constant so that you just have a single solution. Whatever makes it simpler, like set the constants equal to 0 or set the constants equal to 1, whatever makes it simplest. Right? But just find any particular solution. Once you've done that, the general solution to the equation Ly equals f is given by y of t is particular solution of t plus y home of t where y home of t is the general solution to the homogeneous ODE L of y equal to 0. Okay, so you just need to find one solution, any solution, to the non-homogeneous one, and then the general solution to the non-homogeneous equation is given by the one you found plus the general solution to the homogeneous ordinary differential equation, right? So we spent last class talking a lot about how to find solutions to the homogeneous ordinary differential equation. So this theorem says that to find the general solution of the non-homogeneous, we just have to figure out how to find one solution, any one. Okay, so let's go ahead and prove the theorem. Okay. So the operator notation makes this proof easy to write down. Okay. So first note that every solution, well, rather, every function that you can write as a particular solution plus a homogeneous solution is a solution of Ly equals f, since L of y part plus y home, well, L is linear, so that's just L of y part plus L of y home, right? But L of y part is y part is a particular solution, so L of it is equal to f, and y home is a homogeneous solution, so L of it is equal to 0, and so we end up with f. Next, suppose that y is any solution of Ly equal to f. We want to check that y minus the particular solution solves the homogeneous equation L of y equal to 0. And indeed, if you plug in L of y minus y part, then you have, well, L of y minus L of y part, right? But both of these are solutions of the non-homogeneous system, so we get 0, just like we wanted, right? So the difference solves the homogeneous equation. Okay, so let's do an example. Let's use the same R that we were using before the theorem, because we've already worked out what the general solution of the homogeneous system is. So let's say R is take 2 derivatives minus 4 times take 1 derivative plus multiply by 13. Suppose that's R, then we want to find the general solution to the equation R of y evaluated at t is just t, right? So here our forcing function is just the function t. Okay, so the theorem tells us that we need to find a particular solution. Right? Once we found a particular solution, we can just add the general solution of the homogeneous system equation, and then we have all of the solutions to the non-homogeneous equation. Okay, so we need to find a particular solution. Since the right-hand side is a polynomial, let's look for a polynomial solution. Okay, so we're just going to plug things in and try to find something that works. If we plug in, say, a plus bt, we get R applied to a plus bt. Right here, a and b are going to be constants. So if we plug this in, then when you take 2 derivatives, you get 0. So minus 4 times when you take 1 derivative, which would give you b, and then plus 13 times this polynomial, a plus bt. Right, so that gives us 13a minus 4b plus 13bt. Right, so we ended up with this polynomial of degree 1. To get a particular solution, we need, well, the constant term, 13a minus 4b, that should be equal to 0. And the coefficient of t, that should be equal to 1. Right, this system is simple because we can find b from this final equation and then plug that in over here to find a. So a would be 4 divided by 13 squared, so 169. And voila, y part of t equal to 4 divided by 169 plus 1 over 13 times t is a particular solution. Since we already know that the general solution to ry equal to 0 is given by a times e to the 2t times cosine 3t plus b e to the 2t sine of 3t. right, with A and B arbitrary constants, it follows that the general solution to the equation Ry equals T is y of t is, well, a particular solution. So this one, 4 over 169 plus 1 over 13 times t, plus the general solution to the homogeneous system. Okay, we'll stop there and pick it up from there next time.